Okay, so in the last video we talked about electromagnetic waves and the electromagnetic spectrum. So just really quickly, we're going to wrap up talking about electromagnetic waves before we move on to 4.3. So you might be wondering, what exactly is it that is waving in an electromagnetic wave? And this may come as a shock to you or not, but an electromagnetic wave basically contains two different waves in one. Okay, it contains an electric wave and a magnetic wave, hence electromagnetic wave. Okay, so it's actually a combination of two transverse waves that happen in sync, or I guess I should say with a phase difference of 0. So all electromagnetic waves consist of an electric field and a magnetic field that are oscillating, and I'll show you this on the next slide. It's important that you understand what an electromagnetic wave consists of for the next part of this unit when we talked about polarization. So an electromagnetic wave looks something like this. Okay, and so here you can see in pink the electric field is a transverse wave, and in blue you can see the magnetic field is also a transverse wave. And without getting into too much detail about the physics behind it, because it's actually a little bit complicated mathematically, basically the way this works is as the electric field changes, it generates a changing magnetic field. As the magnetic field changes, it generates a changing electric field, and so the process just kind of repeats itself. And again, I'm not going to go into too much detail about how electromagnetic waves work, but they always consist of these two pieces. Okay, notice that the direction of travel is perpendicular both to the oscillation of the electric field and the direction of the magnetic field. Okay, so here you can see the electric field is kind of going up and down. The magnetic field is kind of oscillating in and out of the page, but the direction of the wave is actually to the right here. Okay, at a 90-degree angle to both the electric field and the magnetic field. Okay, and this is kind of a poor animation trying to show you that idea. Okay, how these two pieces kind of build on each other. And then here you can see how an electromagnetic field compares to a mechanical wave. And then this is just a lizard riding the electromagnetic wave. Okay, so it looks kind of weird to see an electromagnetic wave in action because, again, it's two transverse waves kind of happening at the same time. So that's what an electromagnetic wave is. We'll talk more about that when we talk about polarization, because we'll be focused on the electric field part of the electromagnetic wave. Okay, so let's move on to topic 4.3. Just a quick review of 4.2. At the end of 4.2, which we just finished, you should be able to explain the motion of particles of a medium when a wave passes through it for both the transverse and longitudinal cases. You should be able to sketch and interpret displacement distance graphs and displacement time graphs for both transverse and longitudinal waves. You should be able to solve problems involving wave speed, frequency, and wavelength. And you should be able to investigate the speed of sound experimentally, although we did not do that one because we're not doing any labs right now. Okay, so that is 4.2, traveling waves. Let's move on to 4.3, which is called wave characteristics. Okay, now 4.3 is the last section that's going to be on this unit, and then 4.4 and 4.5 are going to be their own separate unit. Now, both 4.3 and 4.4 discuss common behaviors we see in almost all waves. Most of the concepts that we're going to talk about apply to all waves, although one in particular applies only to transverse waves. Okay, knowledge of wave properties and wave behaviors is important, not only because waves are obviously prevalent in nature, but because we can identify the nature of a phenomenon based on the property it exhibits. And I will talk more about this later, but basically what I'm talking about there is that historically speaking, the way we actually discover that light is an electromagnetic wave is because we knew about wave behaviors, and we happened to do an experiment that I'll talk about in the next unit that basically showed that light has this type of behavior and therefore is a wave. Okay, that's kind of how we learned that light is an electromagnetic wave. So anyway, let's go to 4.3. So 4.3, there's not a ton of stuff in 4.3. We're going to talk about wavefronts and rays real quickly. We're going to talk about amplitude and intensity, and then we're going to talk about superposition, and the last thing is going to be polarization, which out of everything in here is probably the most difficult, although it's not super difficult. Okay, at the end of 4.3, here's what you must be able to do. You must be able to sketch and interpret diagrams involving wavefronts and rays. You must be able to solve problems involving amplitude, intensity, and the inverse square law. We'll talk about that here in the next few minutes. You must be able to sketch and interpret the superposition of pulses and waves. Describe methods of polarization. Sketch and interpret diagrams illustrating polarized, reflected, and transmitted beams, and then solve problems involving Malice's law. And those last three all have to do with polarization. So in this video, we're probably only going to talk about the first two, maybe the first three of these. Okay, but we are getting pretty close to the end of the unit here. Okay, now as far as what else you need to know as far as guidance goes, the IBs does say that students will be expected to calculate the resultant of two waves or pulses both graphically and algebraically. That has to do with what's called superposition that we'll talk about later. And then methods of polarization will be restricted to the use of polarizing filters and reflection from a non-metallic plane surface. Now in 4.3 there's only three, I don't even want to say equations, but three things given to you. Now the last one, this equation here, the one that has the cosine squared theta in it, that's what's called Malice's law. That has to do with polarized light, and we'll talk about that in a future video. These first two have to talk about intensity. Notice these are not actually equations, these are proportions, because this little symbol here, remember, is the proportional symbol. So as we'll see here in a bit, this first one is basically saying intensity is proportional to amplitude squared, and intensity is proportional to, or inversely proportional to distance squared. Okay, so remember when we talk about something being proportional, we mean basically it's equal to some constant times that value. Okay, so we'll see that later on, but those are both given to you in the data booklet. So the first thing we're going to talk about is wavefronts. Okay, so imagine, a drop of water falls in a lake or in a cup or something. Okay, and it creates a ripple pattern. Now, to simplify drawing this wave, because obviously it's happening in 2 dimensions, we could draw its wavefronts. Okay, and wavefronts basically show, for transverse waves, wavefronts basically show where the crests of the waves are located. Okay, so for example, for this type of situation, you can imagine the circle ripple patterns going outward. We would draw the wavefronts kind of sort of like this picture right here. Okay, where these yellow rings, okay, this is what we call wavefronts, represent the crests of that wave. Okay, and so in this way we can kind of draw the wave 2-dimensionally without worrying about trying to draw it 3-dimensionally, if that makes sense. And so everywhere you see a wavefront, by convention, that is located at a crest, or for a longitudinal wave, that would be located at a compression. Now, wavefronts don't have to be these circles, they could also be drawn as lines. As you can see here again, if you just imagine like a water wave kind of viewed from the top, right? These yellow lines represent the crests, and so if you want to, then you could measure the distance between two wavefronts, and then that would be the wavelength. The wavelength by definition. Okay, so that is one way to kind of visualize waves. Okay, with wavefronts. Notice that wavefronts are always perpendicular to the wave velocity. Okay, now the other way to draw waves is using what's called rays. Okay, now before I show you what a ray looks like, I do want to point out that it is possible for wavefronts to be bent by obstacles. Either going around an obstacle, or obviously this is like a lens. What you're seeing here is basically light being transmitted through a lens, and the wavefront kind of bends as it goes through the lens and it becomes more focused. Now, the other way of drawing waves besides wavefronts is with what's called rays, which basically are always perpendicular to the wavefronts and kind of indicate the direction of the wave. So for example here, these purple arrows represent rays. Okay, and rays are parallel to the wave velocity. Now, which one that you would draw depends on kind of the context of the situation. A lot of the time when you're dealing with light, you draw rays. And a lot of the time when you're dealing with other waves, you draw wavefronts. But really, it's two ways of looking at the exact same situation. And I don't think there's any new information on here. It says rays are most commonly used in dealing with electromagnetic waves, but that doesn't have to be the case. Okay, again, two sides of the same coin, two different ways of drawing waves. Okay. And I said this before, for a longitudinal wave, you would draw the wavefronts at the areas of compression. Okay, so for example, here you can see a speaker emitting sound. This is very clearly a longitudinal wave. You can see it traveling outward. And so if you want to draw this wave two-dimensionally, you would draw the wavefronts kind of like this, and these concentric circles going outwards. And then if you want to draw the rays, you would draw them, like that, always at a 90-degree angle to the wavefront. Okay, so that is wavefront and rays. So let's talk about intensity. Okay, now this is a little different of a concept to talk about. So make sure you take really good notes and listen carefully over the next few minutes. So imagine going back to the drop of water. Okay, a drop of water falls in a cup of water or something. It creates a ripple pattern traveling outward. Now, as the wave travels outward, think about what happens to the size of the wave. Okay, and I guess when I say the size of the wave, I'm talking about the amplitude of the wave. So think about what would happen to the amplitude of the wave, not the physical size of the wave. Obviously, as the wave travels outward, the entire wave is going to get bigger, but the amplitude of the wave. Okay, so this kind of leads us to the concept of intensity, which we'll talk about on the next slide. Hopefully what you said is that as the wave travels outward, the amplitude of the wave decreases. And basically that has to do with the energy of the wave being more spread out. So first let's talk about just what do I mean by intensity. Okay, so intensity of a wave is the amount of power transferred per unit area by that wave. Okay, now the per unit area, if it's power per unit area, that would mean that the units of intensity are typically going to be watts per square meter. And we will see that again in future units, especially in topic 8 when we talk about solar energy. So just to give you a really simple example of intensity, let's say you have a part of your roof that has a solar panel on it. And let's say a patch of my roof receives sunlight with an intensity of 250 watts per square meter. Okay, so watts per square meter, if you look at the units, watts per square meter, that is the unit of intensity. And then it says if I have a solar panel that is 1.4 square meters in area, I want to calculate the rate of energy delivered to the solar panel. Okay, rate of energy is power. And so this question is basically asking you, what is the power delivered to the solar panel? Okay, so just based off of the units, okay, watts per square meter, intensity is basically power per unit area. And so if I know the intensity is 250 and I'm looking for the power, all I would do is multiply. Okay, so I would just stick that into my calculator. And by the way, we're not going to get into it now, but later we'll talk about how this is not actually the true amount of power that you get from the solar panel, because you have to worry about efficiency and stuff like that. Okay, but I get 350 watts, which is not a lot, but it's enough to power a couple light bulbs, maybe your computer monitor or something like that. It's not too bad. Okay, so that's basically what we mean by intensity. Okay, power per unit area. Okay, so pause there if you need to take more notes. Okay, but this is not the only context that we talk about wave intensity in. Okay, so now let's go back to that situation we talked about before, how as a wave travels outward, the amplitude decreases because all that the energy the wave has is spread out over a wider area. And so we're mainly going to focus on spherical waves, which is a wave that basically projects outward with spherical symmetry. In other words, the energy goes out equally in all directions in space. And so imagine, I don't know, you can imagine the sun, you can imagine like a speaker, but something is emitting some type of wave. Let's just make it concrete. Let's imagine, I don't know, a light bulb or something. Okay, my light bulb looks like a hairy potato, but that's okay. Okay, so imagine a light bulb, and the light bulb is emitting electromagnetic wave equally in all directions. Okay, so if you were to draw the rays for that situation, it would look something like this. Okay, now listen very carefully to what I'm about to say. The light bulb puts out an energy per second that is P. Okay, that's its power. Right? If you get a 100-watt light bulb, it's putting out 100 joules per second. Now, if I imagine a sphere surrounding my light bulb, okay, it looks like a circle, but you have to think in 3 dimensions. If I imagine a sphere surrounding my light bulb, let's say that sphere has a radius r, then the intensity out here along the surface of the sphere would be P divided by 4 pi r squared. Now, where did that come from? Well, number one, a sphere has a surface area. The area of a sphere is 4 pi r squared, and intensity is power per unit area, so that is where that is coming from. Now, basically what this is saying is that all the power that the light bulb puts out, all the energy it puts out per second, has to go through the surface of that sphere at some point. Okay, and so as I get farther from the light bulb, let's say my sphere is all the way out here with a bigger radius, the amount of energy going through my bigger sphere is the same amount of energy, except that now that energy is being spread out over a wider surface area. And so the intensity is going to decrease as I get farther and farther away from the wave source. And if it's a spherical wave, it's going to decrease inversely with the distance squared. Now, in the data booklet, there is an equation that looks something like this. This is what I'm talking about here. For reasons I don't really understand, but it doesn't really matter. I like to use r for distance. They like to use x. But basically, it's the same thing. Even if you write it, I equals p over 4 pi x squared. Okay, remember, the proportional symbol just means it's equal to some constant times that thing. Okay, so here the constant would be power divided by 4 pi. And it's basically just showing you that, intensity depends on distance. If you double the distance from the wave source, you decrease the intensity by a factor of 4. Okay, think about that. If you double the distance from a wave source, you decrease the intensity by a factor of 4, because 2 squared would be 4. Okay, likewise, if you triple the distance from a wave source, you're going to decrease the intensity by a factor of 9, because 3 squared is 9. And so that's basically how intensity works. Pause there if you need to look at that some more. And I apologize for the bad pictures, but I'm going to erase this. Okay, this picture is a little bit better, and you can kind of see the visualization of that energy as you get farther and farther away, it's spread out over a bigger area. This, by the way, is what is an example of what's called an inverse square law. Okay, inverse just means like 1 over that something, and squared just because distance is being squared in the equation. Okay, and so for spherical waves, this is the relationship that you're going to use to find intensity. Okay, examples of a spherical wave which I've seen before, again, water waves from a water droplet, sound waves from a speaker, light from a light bulb. Okay, there's lots of different examples of spherical waves. Okay, so in the data booklet, just think intensity is inversely proportional to distance squared. If you actually want to do the calculation, it would be power over 4 pi r squared, where r is the distance that you are from the wave source. Okay, so let's go to the next slide. Take a look at some examples. Okay, so this example says a 200-watt speaker projects sound in a spherical wave. Find the intensity of the sound at a distance of 1 meter and 2 meters from the speaker. Okay, now, pretty easy calculation. For the first one at 1 meter away, remember we're doing, sorry, not P equals, we're doing I equals P over 4 pi r squared. And so for the first intensity, let's call it I1, the power is 200 watts, and we're dividing by 4 pi times 1 squared. And so I will put that into my calculator. 200 divided by 4 pi, and I get 15.9 watts per square meter. Now, I could use the same equation to find the intensity at 2 meters. However, I should also be able to immediately tell that if the distance is twice as much, the intensity should be a fourth of this value, so somewhere around 4 watts per square meter. But let's see for ourselves. 200 divided by 4 pi times 2 squared. Again, I plug into my calculator, 200 divided by 4 pi times 4, and I get 3.98 watts per square meter. Okay, which you can just visually see is about a quarter of the original intensity. Okay, so a lot of the time, they'll be asking you questions like, if the distance doubles or triples or is a quarter of the value, how does the intensity change? And so for those types of calculations, you don't technically need to do calculations with the equation itself, but you're just looking at how things relate to each other. Okay, in other words, given this intensity right here, if all we knew was that the distance doubled, I should be able to get this answer without actually plugging numbers into this equation. Okay, so pause there if you need to look at that some more. This is just kind of showing the work for that. Oh, and by the way, the other proportion that we hadn't talked about yet is that the intensity of a wave is proportional to the amplitude squared. And so without getting into like detail or anything, what you need to know is that amplitude for a wave has to do with the energy stored in the wave. Specifically, the energy in a wave is proportional to the amplitude squared. And since intensity is power per unit area, and power is energy over time, that means it's also true that intensity is proportional to amplitude squared. So in other words, if you had two waves and one was twice as big as the other, like the amplitude was twice as big, the amount of energy stored in the wave would be 4 times as much. Alright, so let's just do another couple examples. At a distance of 18.5 meters from sound source, the intensity is 2 times 10 to the negative 1 watts per square meter. And we're asked to find the intensity at a distance of 26.5 meters. Now there's two ways to approach this question. First of all, we're given distance, we're given intensity. So what we could do is we could find the power of the sound source. And the power from the sound source doesn't change. That doesn't depend on distance. That just depends on the sound source. Okay, so one thing we could do, intensity is power per unit area, is we could just plug in 2 times 10 to the negative 1 equals P over 4 pi 18.2 squared. We could solve for P, okay, just using basic algebra there. Okay, so I'm just calculating that value right now. I get about 860 watts. And then I could plug into the new intensity equation, take that same power, and then plug in my new distance. Okay, so again, I'm just plugging this in to my calculator. And I get 0.097 watts per square meter. Now the other way I could have done this is I could set up a proportion. I could say that, okay, the intensity at position 1 is equal to P over 4 pi R1 squared, where R1 is just, the distance from the wave source to my first point, and the intensity at point 2 is P over 4 pi R2 squared, and I could just divide these two equations by each other. Now, why would I want to divide these two equations by each other? Well, because when I divide this on the left side, I get I1 over I2. And when I divide this right side by this right side, the P cancels because it's the same in both. The 4 pi cancels because it's the same in both. So this is 1 over R squared divided by 1 over R2 squared, which is basically R2 squared over R1 squared. Okay, and now I could just solve for, the intensity at whatever distance I want. So let's say I want to find, so let's just say that this is R2, this is R1, and I want to find I1, then that would just be I2 times R2 squared divided by R1 squared. Okay, and if you plug in, you should get the exact same thing that we got before. Alright, so pause it there if you need to look at that. Okay. And then it says compare the amplitudes of the sound at 18.5 meters and 26.5 meters. Okay, so I'm going to erase what I had before. Okay, so using our last answer, we can also set up a proportion, as you can see here. And you can solve for the ratio A1 divided by A2. Okay, so again, we're just setting up a proportion. Because I is proportional to amplitude squared, that means I1 is proportional to amplitude 1 squared, and I2 is proportional to amplitude 2 squared. I1 over I2 we found in the last problem. Okay. And so by setting up this ratio and then taking the square root of both sides, we can solve for, A1 over A2, and we can find out how A1 and A2 relate to each other. Okay, and so what you should find is that A1 is actually approximately 1.43 times A2. So in other words, between 18.5 meters and 26.5 meters, the amplitude decreases by a factor of about 1.43. Remember, As you get farther from a wave source, of course, the amplitude decreases because that same amount of energy is spread out over a wider area. All right. Okay, so that takes us about halfway through 4.3. Okay, the last two things in 4.3 have to do with superposition and polarization, and then we'll be done with our first waves unit. Okay, I'm going to go ahead and stop this video here, and then in the next video we'll talk about superposition and start talking about polarization. As always, please let me know if you have any questions, and I'll see you guys in the next video.